Hi, I'm Tomohiro from the University of Tokyo, the Virtual Reality Educational Research Center. Today, I'd like to share my research on virtual reality applications using pseudo-attraction force by asymmetric oscillation. This talk will introduce you to some applications using pseudo-attraction force created by an asymmetric oscillation. Let me show some prototypes of haptic displays generating an asymmetric oscillation. We have spent more than 10 years scrapping and building a prototype and conducted some user study to find the best vibration pattern to induce the illusion. There are plenty of haptic displays that provide richer haptic experience than just vibration. Unfortunately, they usually tend to look like the devices on the left pictures, called grounded force displays. So in the grounded force display, both the user and display must be connected to the ground. So it's very hard to apply this technique to mobile devices. So our research goal is to create the sensation of being pulled or pushed in mobile devices. So we selected a stimuli of asymmetric oscillation patterns, which can be used in the mobile devices. And the asymmetric oscillation pattern can induce the sensation of being pulled or pushed. We call it a pseudo-attraction force. The force display is categorized as a tactile force displays because it stimulates the skin by vibration or a dynamic skin stretch to induce motion. So let me show you some examples of non-grounded force displays. One approach, the physics-based approach, uses the torque by distance, control gyro moment, and momentum wheels. They can generate torque sensation without external grounding. However, the conventional displays can generate neither constant nor translational force. On the other hand, there is another approach called perception-based approach. So using this approach, like asymmetric oscillation pattern, these devices can create a sensation of a constant and translational force. So let me show you a video.
If an attraction side attempts to produce an attraction force without being fixed in place, this force by itself will cause movement, and no attraction force will be given. This is why a mobile terminal, while capable of vibrating, does not generate a sense of attraction. However, using a sensory illusion, a person can be given a sensation of force different from the actual underlying movement. But how can vibration feel like an attraction force? Here is the first Buru-Navi prototype. The slider in this equipment moves back and forth in a cyclic manner. If it moves left and right at the same speed, a person would perceive this movement as simply vibration. However, if the slider is made to accelerate rapidly in one direction and decelerate gradually in the other, a person would only feel the former rapid movement. In this way, a sensory illusion is created in which the vibration is felt like an attraction force. Inside Buru-Navi is a mechanical setup like a steam locomotive. But how do gears and cranks navigate a person? The secret lies in the vibrations of weight. When the motor vibrates the weight, the reaction of weight vibrates the overall equipment. This vibration can be felt as a tactile sensation by a person. We prepared two acceleration modes for going and returning. The weight moves in a fast acceleration in one direction and a slow acceleration in the opposite direction. Human beings feel a strong acceleration distinctly, even if it is for a brief moment. On the other hand, if the acceleration is weak, even if it continues for a length of time, it cannot be clearly felt. Therefore, only the vibrations due to a fast acceleration can be sensed. This allows the user to feel that the device is moving in one direction.
So the acceleration pattern can be determined by the length of the linkage using in this prototype. So the output can be calculated by these equations, and the recorded acceleration pattern is shown in the right figures. So using this prototype, we can create a one-directional force sensation. So some collaborator wants to use this system in the navigation system. So we collaborated with the fire department person for the people who are blind or visually impaired, and they want to use this system to tell the correct direction for the emergency situation. So this movie showed the experiment in the gymnasium, and the checkerboard shaped maze, which was built in the as looks like Kyoto city's roadmap. So we asked to the people with visual impairment to walk as they felt the force direction, and the 21 of the 23 participants successfully complete the task of the navigation on the predefined route. So which means that the walking from the entry point to the end point with the four turns. Some participants was not able to perceive the force direction correctly at the corner, but they can recover the route with the force display. In our device, Buru-Navi allowed people with the visual impairments to walk safely along a predefined route at the usual walking speed without any previous training. We also created different types of navigation device using the asymmetric oscillation. So we built the asymmetric audio with turntable. So using the motion capture system, the direction of the hand or devices were measured and change the direction of the force of navigation. So that's why the people can walk on the predefined route. And also we made a tiny small prototype. Let me show you some video.
Over the last several years, we have designed and developed several prototypes to generate asymmetric oscillations. We have recently succeeded in decreasing the size and weight greatly. The small mass inside the tiny black box asymmetrically oscillates. As you can see, if this device is driven on a friction surface, the asymmetrical motion generates a movement because of the difference in static and dynamic friction coefficients. When you pinch the device hardly moves on the fingertip. However, you will feel as if you are continuously being pulled in the desired direction. Even if you are blindfolded, you can tell the direction of the force sensation clearly.
So the prototype shown here is as small as the thumb drive, almost just 90 gram, just very small size. It can be pinchable. And we also implement 2 degrees of freedom version. It means that they can pull the forward, backward, leftward, rightward, just using 2 vibrators inside this cylindrical object. So the vibration pattern is almost the same as the crank slide mechanism, but this was modified to for the vibrators inside this prototype. So we implemented the virtual angling game, and the user can feel the sensation of a virtual fish nibbling on the hook. So when the user pulled up the string, pulled up the Buru-Navi device, they will feel a virtual fish pulling your hand downward. And you can also interact with the virtual fish by moving the weight on the surface of the touch screen. So this is another example of the application using Buru-Navi. So in this application, the user use 2 Buru-Navis, and they can interact with the virtual object and feel the stiffness of it according to the distance between 2 hands. So by moving their hands, and they can feel the reaction force from the virtual object and feel the softness or hardness of the object interactively. So in the virtual reality system, the temporal onset of the visual and haptic information can be varied. So in this case, the preceding visual information can help to perceive the sensation of being pulled or pushed. The future work includes the finding the temporal difference between the visual motion and haptic information. So let me summarize my talk. So this study introduced haptic displays based on the perceptual illusions with potential for VR applications. And I believe that sense of touch is very effective in presenting a feeling of object existence. So to maximize the benefit of haptic displays, utilizing the human characteristics such as the sensory illusion provide us with new cues to develop innovative information displays. And please note that there is a trade-off between the higher fidelity force feedback and spatial workspace. It is important to select the type of the force predicting method. In this case, the ground force display, non-grounded force display, the physics-based, or the perception-based, suitable for the VR application, respectively. And in future, adding other modalities such as vision and audition will create a far richer haptic experience because of the multimodal integration, enabling the VR systems to integrate them easily. Okay, that's it. Thanks for listening.